We're set up now. Maybe. Okay. All right. Welcome to Thursday. Today we're going to be talking about a little bit of new stuff, and then we'll be kind of practicing, and hopefully by the end of today, everybody will have a good sense of what we're doing today. So last time we looked at the periodic table and we talked a little bit about the trends and going across things like that. Today we're going to look at the individual atoms, the particles that make them up, and how we know how many of each particle a given atom has. So when the book talks about this, it kind of goes into this history of how all these things were developed, which is interesting. And if you're interested, you should read it. But we're not going to spend a lot of time talking about that. We're going to focus more on the skills of how do you actually figure this stuff out. Okay, so our basic atomic structure that you may have heard from before has three types of particles that make up an atom. Anybody know what they are? Electrons is one. What else? Protons. Yeah, electrons, protons, and neutrons. I heard them all, so great. All right, those are the three subatomic particles, we'd say, the three particles that make up an atom. Anybody know anything about them? What's some of the differences between them? What's special about them? Yeah. So electrons are negatively charged. So sometimes they're written symbolically as an E with a little net minus sign. Sometimes we use that notation to describe an electron. They're negatively charged. What else? Anything else about electrons that you know? Well, that's okay. The negative charge is the important part. The other thing to know about electrons is very little mass. We'll talk about these mass numbers in a little bit, but electrons are so small compared to the other two, protons and neutrons, that we often treat them as though they just have no mass at all. And they do have mass, but it's so small that it's effectively like they don't have any mass at all. So a tiny amount of mass. Okay, so what about protons? Anybody know the charge on a proton? Yeah. That should be minus one. So protons are positively charged. So they have a charge of +1, we'd say. And does anybody know the mass of a proton? In like grams or kilograms or something, it's extremely small. So it's actually not even given. Let's see. Yeah, it's not even in here. So it's very small. What we do know about a proton is its mass is about 1 AMU, where AMU stands for atomic mass unit. So it's because those things are so small, it's not really useful to use things like grams and kilograms to describe them. So we use this AMU, which is this tiny unit of mass. It's defined as 1/12 the mass of a carbon atom. Let's write that down.
Can you say that again?
Yep. So atomic mass unit. And this won't make sense now, but we'll just put this in here to be clear. So that's not really an important definition. It's just another mass unit that is very small and that makes sense in the context of single atoms. So we say we take an atom of carbon, we split it in 12 equal parts, and one of those 12 is what we call an atomic mass unit. So a proton is about 1 AMU. If you look in the book, if we go out to a few more significant figures, it's actually 1.007 AMUs, but it's about 1. All right. So then neutrons are neither. They are neutral, no charge. And they also weigh 1 AMU, just like the protons. Okay. All right, so those are the different subatomic particles. Let's look about where these things are. So where are the protons in an atom? You know? See some people drawing some shapes. You know what that's called? The nucleus. Yeah, the protons and the neutrons are in the nucleus, the middle of the atom. And where are the electrons? Outside. Yeah. And they're actually pretty far away. We'll talk about that in a minute. So I didn't draw a picture here. The reason I didn't draw a picture, I don't want you to get the wrong idea. We often have this picture of an atom as the nucleus in the center and the electrons going around the outside like big circles, kind of like our solar system. And that's not correct. It's not true. Electrons don't orbit around the nucleus like planets. They exist in these things called orbitals outside the nucleus, these kind of clouds that they can be in, but they don't go in these nice circular orbits. So we're not going to draw that picture. We don't want to extend that misconception. We're just going to say the protons and the neutrons are concentrated in this nucleus in the center of the atom. The electrons are somewhere around the outside. Okay, so that's our different particles. We should also say, let's see if I can find the number for this, so that they're pretty far apart from one another. Where did I just see that number? So the diameter of a nucleus, so how far it is from one side of the nucleus to the other, is about 10 to the minus 15th meters. So that's 0.000015 or 14 zeros and then a 1. That much of a meter, which is a tiny, tiny bit. The atomic diameter, so the diameter of an entire atom, depends on the atom, but it's around 10 to the minus 10th meters. Also a really tiny number. So how do we make sense of that? Well, one way we could say it is that the nucleus, the nuclear diameter and the atomic diameter are about, 10 to 5? So 5 zeros apart, so 10,000 times difference. In other words, if this is the nuclear diameter, you have to go 10,000 times that to get to the electrons, to get to the outer electrons, which is a big difference. If you think about, like, let's say the nucleus was a meter. Okay, so here's our nucleus. That means that our electrons would be 10,000 meters away, or 10 kilometers away, about 6 miles. So if this were the nucleus, the electrons would be 6 miles away. So they're really, really far apart from each other, relatively speaking. And that means that most of everything that we encounter that's matter, that's made of atoms, is actually mostly empty space. So there's only, the nucleus is only here. The electrons are way out in, I don't even know where that would be, just planes or something. So all of that in between is just empty space. All right. So let's figure out how many of each of these things are in a given atom. Does anybody know how you can find that out? The what? Yeah, the periodic table has some numbers on it, and those are going to have something to do with this. We're going to define two quantities, actually three. Three quantities we'll do here. The atomic number the mass number and the atomic mass. Now these words are pretty similar, especially because the third one has words from the first two in there. So we're going to do what we can to try to make these, keep these straight. The first one's pretty straightforward. The atomic number is the number of protons and the atomic number defines the atom. So it tells us what that kind of an atom is called. We see the atomic numbers in blue on this periodic table. On other periodic tables, they may not be in blue, but they're always whole numbers. They're usually at the top, and they count up starting at 1 at the top left corner, all the way up to whatever, 118 at this point. Is what's been discovered. So those numbers all refer to the number of protons in the atom, and they define the atom to be what it is. So a carbon atom always has 6 protons, and any atom that has 6 protons is called a carbon atom. So it goes either way. Carbon always has 6, a 6 always has carbon. So when we talk about adding or removing protons or changing things, we would actually change the identity of the element if you change the number of protons in it. So you turn it from one thing to something else. The mass number is the number of protons and neutrons. So the number of protons added to the number of neutrons. Is this one on the periodic table? It's not. It's not, because the mass number is always a whole number, just like the atomic number. You're just adding up the protons and the neutrons. So if you ever forget about that or can't remember, notice that those red numbers on the periodic table are not whole numbers for the most part. They're decimals. So that tells us the mass number can't really be found on the periodic table. And let's make a note of that. Then the atomic mass, we're going to define as the weighted average, and I'm going to use some words that we haven't defined yet, but we'll come back to it. The weighted average, oops, not atomic. Of mass numbers of isotopes. We'll come back and talk about that in a little bit. But the reason I put this here on this list is that is what is on the periodic table. That is the bottom number in red that you see up there. And that actually doesn't tell us a whole lot of information in terms of which types of particles there are in the atom. So it's a common misconception to say, okay, I know the atomic number is protons and the mass number is neutrons, so I'm just going to look at the bottom number and subtract the 2 and get the number of neutrons. That doesn't quite work. We'll get back to why that doesn't quite work in a little bit. But let's look at this. So we've defined the number of protons. We've defined how we find the number of neutrons from the atomic number and the mass number. What about the electrons? How do we know how many electrons are in a given atom? ideas? No guesses? We use this idea of charge. Let's take a carbon atom, for instance. A carbon atom has 6 protons. That's what we get from the periodic table. What is the total positive charge of 6 protons? Or the total charge of 6 protons? Well, what's the charge of 1 proton? +1. So what's the charge on 6 protons? +6. Yeah. So if you have 6 protons, each with a +1 charge, the total charge of a carbon nucleus is +6. Any atom in its regular atomic state is a neutral atom. So how many electrons would you have to have if you wanted the atom to be overall neutral? 6, right? Because you got 6 plus, you need 6 minus to get back to neutral. So for a neutral atom, neutral carbon atom, six electrons are needed, right? Because +6 and -6 equals 0. So protons are positively charged, electrons are negatively charged. So if you have a neutral atom, you always need the same number of electrons as you have protons. Which means that the atomic number can also be used to give us the number of electrons, assuming that the particle is neutral, that the atom is neutral. All right, so that's how you find out all the periodic, or all the numbers of different atomic particles. Let's practice this by filling in some tables and kind of understanding how we can get one or the other. Before we do that, we just need to look at one more thing, how we write these things. So normally when we write atoms, we just write the symbol. We talked about that on Tuesday. You just write down the symbol. But when we want to specify the amount of mass or the amount of neutrons or protons, we use a different notation where we put little numbers by there. So if we stick with our carbon atom, okay, we just draw a capital C, that's carbon. But we can also put a 12 up in the upper left-hand corner, which tells us that this is specifically carbon with a mass number of 12. The upper left-hand corner gets the mass number. And if we want to be really specific sometimes, we even put the atomic number down here. Having the mass number in the upper left-hand corner could be important, but the atomic number is always redundant. Why is it redundant to show the atomic number there? Why don't we need it? Yeah, exactly. So to be carbon, it has to have 6. So if that number were anything but 6, it wouldn't be carbon. So the C itself tells us that it's 6. The only reason we put that number down there is if we're doing some reactions where that might change. It's nice to see the number for adding and subtracting, things like that. So you'll see that in some of the homework. Other ways that this can be notated, sometimes you'll see like this. So C-12 tells us the mass number is 12, or written out like this, carbon 12. And we're going to see in a little bit that that number can actually change in some different particles. So that's why it's important to sometimes specify that.
I don't understand. Can you tell me why the mass number is 12? I lost something there, how to get the 6 to the 12.
Well, that's exactly it, is you can't. So the mass number is not something that you can just figure out from anything else. I just put that down there as a number.
Okay.
But given the mass number, we can figure out the number of protons and the number of neutrons because they have to add up to the mass number. So if I tell you the mass number is 12, then we know, okay, 6 protons, so it's got to be 6 neutrons, so that adds up to 12. But if I didn't tell you that, there's no way of like magically determining that because all the atoms have multiple different types of mass numbers. So somebody has to tell you that. Yeah. So let's do an example where we look at that and see how that can be told to you, I guess. All right. So this is on page 131. All right, everybody see that table? So here's a table where we've got names of some different elements, some symbols, and then number of protons, neutrons, and electrons. And some of the information is given, but a lot of it is not. And just from the information it's given, we should be able to figure out all the rest of it. So let's see how we do this. We'll do the first row together. How do we figure out the name from just the symbol? Yeah, you have to look it up in a periodic table. So like in your lab notebook or the one in your book or something like that, you have to look that up. So anybody know what's S? What's the name? Sulfur. Yeah, sulfur. S is sulfur, so you would look that up in your table. All right, we got the symbol. How do we get the number of protons? Yeah, 16 on there. We can also get it from the symbol right there on the lower left-hand corner if it's given. So 16 protons. What about the number of neutrons? How can we get that? Right. We know the upper left number there, that 34, is the protons and the neutrons added together. So whatever the difference between 34 and 16 is, that's the number of neutrons. So what is it in this case? 18. Yeah. 16 plus 18 is 34.
Wait, what?
16 plus 18 is 34.
16.
All right, so then the last category is electrons. How do we get the number of electrons? Right, 16. So it has to be the same as the number of protons so that we have an overall neutral atom. All right, because the protons and the neutrons have to balance out. If they don't, then we have a charged particle called an ion, and we'll get into those later. All right, so given that example, see if you can complete the rest of the table. You'll need a periodic table to look at for the names and the symbols. But other than that, you should be able to put those in or at least give it a try. And then we'll go through it and see where you might have gotten stuck. All right, let's take a look at these. So in the next row, the second row, you're not given the name or the symbol, you're just given the number of protons and the number of neutrons. So how do we figure out the rest of it? What was the name of this one? Did you find this one? I heard it somewhere. Nickel, yeah. So we look, number of protons is 28, that's the atomic number. So you look it up and you see that that one is nickel. The atomic symbol for nickel is Ni, but we also have to fill in those numbers. So the bottom one is the same as the atomic number. What's the mass number for nickel? 62, right. So you get that by adding up the protons and neutrons. And then what's the number of electrons? So it's got to be 28 because, again, it's a neutral atom. So the protons and the electrons are going to be the same. Okay, third row. We've got magnesium, that's Mg. We're not given the number of protons, so how do you find the number of protons? Look up there.
12.
Yeah, so it's going to be 12. And now we can fill in those numbers, 12 down here, and what goes on top?
26.
26, yep. Protons and neutrons added together. And what about the number of electrons?
12.
Right, still 12. Okay, last row, we just have the atomic symbol, just like the first row, we fill in everything else. So which element is that? That's radon. And the number of protons? 86. Number of neutrons? 134. So you get that by subtracting the mass number from the number of protons. And then the electrons, same as the protons again, 86. Okay, so keep in mind that in order to be able to do all of those, we had to be given some information in each row. So you can't just say, I can't just name an element and have you fill everything out, because you need to be either given the mass number or given the number of electrons. The reason for that is something called isotopes. Isotopes are atoms with the same number of protons but different number of electrons. Or not electrons, I'm sorry, neutrons. All atoms have different isotopes. Isotopes does not just mean like different ones or unusual ones, it's all of them together. So if we go back to our carbon example, the most common form of carbon in nature is carbon-12. So that would be carbon with 6 protons, 6 neutrons, 6 electrons. But there is also in nature carbon-13 and carbon-14. Carbon-13, since it's still called carbon, still has 6 protons, and so does carbon-14. The difference comes in the neutrons. Now we've got 7 neutrons, or 8 neutrons. And then since neutrons have no charge, that doesn't affect the number of electrons.
So then, different number of electrons, different number of neutrons. Because you wrote electrons.
Oh, yes, you're right. I'm sorry. I keep wanting to say electrons today. Thank you. Yeah. Same number of protons, but different number of neutrons. So all atoms have some different isotopes. And that's why we need to be told either the mass number or the number of neutrons. So I can't just say how many neutrons are in a carbon atom. I have to say how many neutrons are in an atom of carbon-12 or carbon-13. So where that red number comes from then is an average of the different isotopes that exist in nature. For carbon, just as an example, carbon-12 accounts for about 99% of the carbon in the world. Carbon-13 is about 0.9%. These are approximate numbers. Carbon-14 is, it's really less than that, but we'll say about 0.1%. So if you average those together, a weighted average, you get 12.011. And that's where those numbers, those red numbers on the periodic table come from. Those are the atomic masses, which are the averages of the isotopes. So let's look at bromine, number 35 on the periodic table. You'd see that its atomic mass is 79.904, which is pretty close to 80. So it's tempting to think that the most common isotope of bromine is bromine 80, and then start calculating your numbers accordingly. And that's wrong. Actually, bromine 80 doesn't exist. There's bromine 79, there's bromine 81, and they're about 50-50 in nature. So those average out to come to 80, but there is no actual bromine 80. So you can't use the periodic table to determine the number of protons or which isotope you're dealing with. And it's really tempting to do that, but make sure you don't. All right. Okay, let's try some more of these. So this idea can be asked in a couple different ways. We can do a table like that, or we can get some descriptive questions like this. All right, see if you can write those four. Again, you might need a periodic table with the names on it for reference. All right. Let's look at these. So I looked around, kind of looked like people were on the right track. So the symbol for an aluminum atom with 14 neutrons, we're going to write Al. Okay. We're going to look up the atomic number, which is 13. Put that symbol here. And then what are we going to put up top? 27, right. Okay, the most common mistake I saw was people putting 14 up there instead of 27. And that's a really common mistake that everybody makes at some point or another. But just try to keep in mind that's the mass number, that's the protons and the neutrons added together, not just the neutrons. So the mass number goes on top, not just the number of neutrons. All right, so B, you're not told what atom it is, but you are told the atomic number is 26. So what atom does it have to be? Iron. How do you know? Yeah, because you look up 26, right? It says Fe. So we go Fe, 26, and what do we put for the mass number there? 58. Right, the neutrons and the protons added together. It's tempting, again, since you're already looking at the periodic table, to go, oh, 56, because the red number is 55.8. That's kind of like 56. So it's tempting to just put 56 up there. But remember that those red numbers are not the mass numbers. The mass numbers are dictated by how many protons and how many neutrons. So you got to add them together to get that. All right, strontium atom with 50 neutrons. Strontium is Sr. We look it up on the periodic table. We get 38 for the protons, 50 neutrons. So what's our mass number? 88, right? 50 plus 38, 88. And then finally, mass number of 72 and atomic number of 33. That's easy since we're just told those numbers. We can just look that one up and find that it's arsenic, As. Okay, so that's how you do that. There is a ton of practice in that section of the book, so make sure you take a look at that. The last thing we're going to do today, for the rest, yeah, go ahead.
So going back to an aluminum atom with 14 neutrons, but
Yeah.
do we have it over 13?
Right. Because the atomic number for aluminum is 13. If you look up aluminum on the periodic table, it's number 13.
And then what is it? 14 neutrons.
So 13 protons and 14 neutrons added together is 27. And so the mass number is 27. You put those together. Right. So the other part of the atomic structure we're going to look at today, and this will be the end of chapter 4, is how the electrons are arranged in an atom. And we call that the electron energy levels. What do you think, based on all the stuff we've talked about, what do you think is the most stable configuration for an electron to be in? Do you think it wants to be closer to the nucleus or further away from the nucleus? What's more stable for an atom? If the electrons are closer to the nucleus or further away from the nucleus? You just guess. Get closer. Why closer? You're right. Any idea why? Anybody else? Why would the electrons want to be closer to the nucleus? Well, let's think about the charges. What's the charge on the nucleus? It's like, well, I mean, it depends on the nucleus, but it's positive, right? Because that's where the protons are. The neutrons don't have a charge. The electrons are negatively charged. So negative and positive charges attract each other, right? So if those are closer together, that's going to be a stronger connection, a better situation, a more stable picture for the atom. So what this means for us is that as an atom gains electrons, those electrons are going to start close to the nucleus and then move farther away. And as they move farther away, they're going to increase in energy, meaning that they're going to be more able to be taken away or to do stuff that we're going to talk about in the next chapter, like connecting, bonding, that kind of thing. So what we do is we place electrons in energy levels starting closest to the nucleus and those are going to be the lowest energy. Now, all the electrons don't fit in the same spot. So these different energy levels are going to have different numbers of electrons. And we can figure that out in a diagram like this. So the book uses a slightly different way of drawing this. You may have learned a different way in the past. Whatever works for you is fine. I've had success with this one. So we're going to look at it kind of like a graph, where our y-axis is energy, low energy to high energy. And we're going to look at 3 energy levels. 1, 2, and 3. This also correlates with distance from the nucleus. So 1 is going to be the closest to the nucleus, 2 is farther away, 3 is farther away. Okay, and we're going to draw these kind of buckets. One kind of small bucket, and then 2 bigger buckets. And these are going to be our containers for our electrons, where the electrons go. Now these buckets can only hold so many electrons. The first one can hold 2. The second one can hold 8. And the third one can hold 8. Now, if you go on in chemistry, you'll find that that's not the whole truth. There's some other complicated stuff going on, and it doesn't just stop at 3. And go take some more chemistry, and you'll figure all that out. But for this class, we're going to stick to these 3 buckets, these 3 energy levels, and their maximum numbers of electrons. So you can have a max of 2 here, max of 8 here, and a max of 8 here. If you remember 2, 8, 8, pretty good. Okay, so let's try this out on an actual atom. Let's say carbon. So how many electrons are in a neutral carbon atom? 6, right? Same number as protons. So we've got 6 electrons. We're going to set up our buckets, 2, 8, and 8. And we're going to put those 6 electrons in the buckets, starting from lowest to highest. So we go 1, 2, 3, 4, 5, 6. And that's all of our electrons. So we would say that carbon has 2 electrons in the first energy level and 4 electrons in the second energy level. Another one. Silicon. How many electrons does silicon have? 14, right. So we're going to do the same thing. One, 2 in the first bucket. 3, 4, 5, 6, 7, 8, 9, 10. So 8 in the second bucket. And then 4 in the third bucket. Okay, and that's called our electron configuration for silicon. So why is this important or useful to be filling these things up in these buckets? Well, we're going to define 2 more terms that will help us out. The valence electrons we're going to define as electrons in the outermost or highest energy level. And then the core electrons are all the rest. The reason we make this distinction is because those valence electrons, the ones that are in the outermost energy level, are the ones that do all the stuff. So all the things we're going to deal with in the next chapter, and the next chapter, and whatever, are all based on the valence electrons, because the other ones are too close to the nucleus, they're held tightly, they don't go out and do stuff, they stay home. So we really only care about the valence electrons when we talk about the chemistry that atoms are engaging in. So it's important to know which ones they are and how many there are. So let's go back to our diagram here. And we can see when we build these things up, we can now figure this out. So we can say, all right, the valence electrons are the electrons in the outermost energy level. So which electrons are the valence electrons for carbon? The what? Yeah, the 4 in that highest bucket, the highest filled bucket, right? The highest one here. So these are the valence electrons, and we would say carbon has 4 valence electrons. And then the rest of them are the core electrons, so carbon has 2 core electrons. All right, what about silicon? How many valence electrons does silicon have? 4 again, right? Everybody see that? The highest bucket has 4 in them. It's a different bucket this time, but that's still the highest one. So we're going to say that that also has 4 valence electrons. And how many core electrons? 10, yeah. All the rest are the core. So even if they're in multiple buckets, those are all going to be the core electrons. All right. So what might we say is a similarity between carbon and silicon? They both have 4 valence electrons. And since the valence electrons control the chemistry, that means that chemical things that carbon does, silicon should also do. And that actually ends up turning out to be true. So carbon makes 4 bonds generally, for instance. Silicon also makes 4 bonds. There's lots of properties that they share. They can make a lot of the same types of structures. And so that's why it's important. Now, which group number are carbon and silicon in? Yeah, 4A, right? So is there maybe a shortcut to figuring out how many valence electrons are in an atom? What do you think it is? Yeah, the column number. The column number is a shortcut to the number of valence electrons. Unfortunately, it only works for the A's. That's why there's A's and B's, because the B's are the transition elements. They do weird stuff. But for the A's, it works. Any of those A's, you can build up the buckets like this. It gets a little weird in the fourth row down, so we're not going to do that in this class, but the column thing still works. So we would still say that like iodine down number 53 has 7 valence electrons because it's in 7A. You can also find that by building up the buckets. So that's where this idea of the periodic table comes from. It's periodic because as you cycle through these rows, every time you get to the row where you've got 4 valence electrons, you're going to have some similar properties. They're going to be different from the ones with 5 valence electrons, and then the ones that all have 5 have some similar properties. So that gives us the organization of the periodic table. That tells us where these things are and how these things fit in the different levels. You'll notice that in the first row, there are 2 elements, H and HE, and there's 2 spots in the first bucket. In the second and third row, there are 8 elements going across, 8 spots in the bucket. So you can actually draw these diagrams without even counting up, just by looking at the position on the periodic table and saying, oh, okay, that one's in column 5 in the third row. So I'm going to fill my buckets and then have 5 in the third bucket. So that all goes together, and that's where that comes from. Yeah.
What if you were to do like RB in this place?
Yeah. So I said it gets weird, right? Yeah. Yeah. It gets different later. So this doesn't actually work past the third row. It works into the first 2 spots of the fourth row. You can have a 4th bucket, but everything else, it doesn't quite work. The column number thing still works. So you could say RB was your example, right? Rubidium is 37. So you could say rubidium has 1 valence electron and 36 core electrons because it's in the first column. But you couldn't count them up nicely in the buckets like this because it doesn't quite work that way. Yeah.
Just curious, like those diagrams, is that the same as like how they
Yeah, and that works too. So if you like the rings, go for the rings. Yeah. I like the buckets, not for any particular like philosophical reason. I think that it's nice to think about it as energy levels, like which ones are higher energy. But the rings tell you more clearly which ones are further away from the nucleus. And those things both are kind of the same. So whichever you like. And actually, when we do this lab next week, I think the lab tells you to do it with the rings. So however you like to do it, as long as you can figure out how many valence electrons, how many core electrons, we're good. All right, other questions? Okay, so in the next chapter, we're going to look at, so we're going to skip chapter 5. We'll come back to it later in the semester. We're going to jump to chapter 6 next week, and we'll be looking at what happens when electrons get lost or gained, looking at ions and the things that they do, and how we name these structures, kind of getting into some more of the chemistry. We'll do that in chapter 6, and then in chapter 7, we'll get into some more fun calculations and conversion problems. I know everybody likes those. This time we'll be using something called the mole, and we'll be well on our way. So that will take us up to the first exam, I believe, will be chapter 7. Probably just chapter 6 for the first exam, which is a week from Tuesday, right? Or 2 weeks from Tuesday. What? The week of September 18th? Okay, so it would be, yeah, because it's always during lab period, so we'll have our exam on that Tuesday of that week. All right. Sounds good. Okay, we got about 10 minutes left, so if you've got questions or other things you want to go over, you can stick around and do that. Otherwise, have a good weekend. I'll be in my office after this if you have other questions. And I'll be here tomorrow morning if you want to come in also.